Good morning. Welcome to the Knowledge Series. Today under the course of EC 407 Computer Communication, we are going to discuss in the area related to the IP numerical examples. I believe that you have gone through my earlier series where I have discussed about the network theory and IP numericals concept. So here we are going to see the numerical examples. Before starting, let me refresh you with the class full addressings, where different classes A, B, C, D and E with the starting address ranging from 0 to 127 for A, B from 128 to 191, C from 192 to 223, D from 224 to 239 and E from 240 to 255. The easy way to remember, as I have already informed to you, is that starting at a 0 to 127, so you can think in a vertical way: 0, 128, then 64, 32 and 16. By remembering that one, you feel this one 0 to 128, that means 0 plus 128, then plus 64, 192 you will get, plus 32 you will get 224, plus 16 you will get 240. Then corresponding to that one you should write, since it is 128, you will write here 127, 192, 191, 224, so you will write 223, 240 you will write 239, and since it is a last address, so every bit should be 1, that is equal to 255. Let me show you once this subnetting, how the subnetting tries to create the different values, and how you can able to understand how this value is being created for the 1 subnet, 2 subnet, 3 subnet or 4 subnet, whatever forms it is being put across. So if you try to see the case with respect to the 3 subnet or a 4 subnet, always we have to go with the masking, and thereby from the masking we will be able to get it. So in place of masking, I am putting in the form of a bit also, you can understand. Single network is shown with the IP address showing in a decimal from 200.1.2.0. So when it is divided into two parts, we have got a range of 200.1.2.0 to 200.1.2.128. Now how it was received, because when we are doing the subnetting, we are going for the subnetting with respect to the case where we are considering the network ID as it is, and from the host sections we try to create the particular masking. Masking we create for the network side, and in the host side we try to borrow the bits. So here in this case 1 bit was borrowed, so the MSB, if it is a 1, so 10000 if it is you are doing with respect to the because 1 bit has already borrowed, so 7 bit will be there. In the 7 bit it is showing as a 128, so automatically it will be giving you the final values as 128. So that is why we try to get the value of 128. Now once it is start from 128, this one how up to what extent it will go? It will go up to 255. So that means it start from 0000. That means it start from 0. It will go up to 127 here. From 128 it start from here. It will go up to 255 in this particular scenario. So that is what we try to see in the case of this subnetting mask with respect to the 2 bits. So that you have to keep it in your mind, that how this particular formation is being taking place. Now if you are going with respect to the case of 3 subnetting, you try to see this. You are borrowing one from the MSB. So under that particular scenario, so you will be having a 1 here, and you are borrowing a bit from the step 2, that is you are borrowing from, in this case, so it becomes 0 in this particular scenario. So you will be having a case with respect to the bit which is either a 0 or a 1. So if it is a 1 0 scenario, if it is a 1 0, you just think like if it is a 1 0 and the remaining 6 bit, so if it is a 1 0, you are going to get 128, and if that bit becomes 1, so that is a 1 1 1 1 0 0 0 0 0 0, so that is equal to 192. So that is what we try to see here. By borrowing from here, we put it as 1, but this one you are taking it is a 0, but from 0 it can go up to 255 because this is already on the high side, so this 0 can become 1, so that can go up to maximum 255. That's why when it become 1, the whole bit becomes 192. So that's how the subnetting scenario also changes with respect to this one. That means you can try to see here. Earlier it was one address in which everybody was using. So only one. It is just like you think that there is a one pen. Pen is there, and that pen is used by everybody. Here, in place of one pen, we divide the. So let us take pencil. We divide shared by everybody. Now here, the one pencil is divided into two parts. We cut the pencil into two parts and then given. So one pencil will be using for this group, this, and another will be for this group. Here, one pencil is used by this group, and this pencil is divided into two parts. So that is two parts. So this will be used by this number of people and this number of people. What is it? What you understand? That means this is a network. This is a network. In this network, one address is given. In this network, one address is given. In this one, in the one network, one address is given. And inside that one, many hosts are there, or many devices is there that is using that common this address. But because of the because of the advancement in technology and more number of devices in the IoTs are emerging out, we cannot go with the single address. We have to give a unique address or independent address. So that's why IPv4 is having a limitation up to 32 bit. So, but when we go for IPv6, it is a seamless manner. So automatically you will be finding a large number of users can be very easily occupied in the case of IPv6. So that's how you can find a difference between IPv4 and IPv6. So here the subnetting is trying to divide the IP in such a way that more number of hosts can be able to access this IP address. Now let's see the examples. Now here in this example, the example 1, change the following IPv4 address from a binary number to a dotted decimal number. So this is your binary number, and this binary number is divided into is been shown in the form of a decimal. So decimal is 192.11.11.239. So when you have this binary number, if you are showing in the form of a decimal number, you represent in this way. So you take the 8421 representations and try to sum up whichever is equal to 1. Second example, convert the IPv4 address from a dotted decimal to the binary decimal. So you have this dotted decimal. So let's take a 56 divided by 2. You get a remainder 0. Another 28 divided by 2. So you get a remainder 0 means it is easily divisible, not remainder. It is easily divisible. That's why 0. Easily divisible 0. Easily divisible 0. It is not divisible by 2. That's why it is 1. It is not divisible by 2. It is equal to 1. So final quotient is getting. So here you will be reading from the right to left. So it is 1 1 1 0 0 0 plus another 2 more MSB zeros. So that is what we shown over here. So this is how this particular representation of a dotted to binary is being shown. Example 3. Now in this one, the error, if there is any error in the IPv4 address, that is being to see in this example. So you have to remember that in the binary representation, in the decimal representation, you cannot show in the form of a 0 at the starting. So that is the there must be no leading zeros on the 045. Means on the 45 you cannot put a leading 0, so it shows a wrong way of expressing, because 0 indicates a binary also. So that's how it creates an error. Now here there are 4 numbers, or 5 groups, 1, 2, 3, 4, 5. That's why 221.34.7.8.25 groups. So that's why this is a wrong. Always IPv4 is having 4 groups. Now here in this case, if you try to see the problem, 301, your maximum decimal value is 255. So this is a wrong IP. That's why each number needs to be less than or equal to 255. Now here you can try to see the representation of IP. Binary is there and the decimal is there. So this is also a wrong way. You cannot have a mixed form of a binary and dotted decimal notations representations. So these are the simple example which will give a eye opening for you. Let's see the another examples. Now in this example, what we are going to, a block of a address is granted to a small organizations. Means a address is there and that was granted to small organizations, and we know that one of the address is 205.16.37.39/28. So from this one you have to identify the first address of the block. So you have to understand, in a block there are several set of address, but one address is given and that address is this one, and you have to identify what is the address, from where to where it should be. This address is not the starting address, you have to remember. This address is somewhere in the middle, but you have to go back and you have to go front to see that where up to where, what extent to what extent you can able to use it. So to do this particular problem, again in the subnetting conditions, you have to take into considerations first 2 factors. One is the class, another is subnetting methods. Now if you try to see this one, 205.16.37, now looking into this one, which class is coming, because class C ranges from 192 to 223. So this is coming under the class C condition. So that is what we can try to see here, class C situations. So here we represent into a binary representation. So this is a binary representation of the all value. So in the class C, this is a net ID, net ID, net ID. This is a host ID. So this is the host ID, since it is clear to you. And what is the slash value? It is showing a decimal value of 28. So that means 28 bits are there in the slash 28 indicates. So what is the IP total number of bits? 32. So we have to, if you want to do this, you have to apply for identifying the first address. What you have to do, you have to subtract the 32 from the value of n. N here, that means any IP address slash n is given, so that we have to do. So here n is 28, 32 minus 28, so it is equal to 4. 4 indicates that you have to have a 4 bits, and that 4 bit should be the rightmost bit, and that should be equal to 0. So if you convert this rightmost bits to 0, that means up to this point, up to this much bit, if you try to convert, so that's what it is being shown here in the form of a zeros. And when you convert this one, automatically this one will become 32. So 32 indicates the starting address. So you can see 205, 16, 37. This is a net ID, and the host ID start from the 32. So for this one, the host ID address. So 32, it will start up to 39. But this is not the finish. Now, if you want to go further, if you are adding this 32 minus n with respect to this 29 by putting ones. That means you do 32 minus n, that is 32 minus 28 is equal to 4. If you convert that 4 and try to put on this right side equal to 1, which is being shown here as 1. If you are doing that one, then it becomes 47. That means your host ID IP number starts from 205 16.37 this is 32, not 28. This is coming as 32 because it is 1 2 3 4 5, so 2 to the power 5 is 32. So this is for your corrections purpose. So it starts from 32 and it will go up to where it will go up to 47, and between that 32 and 47, the intermediate value is nothing but your 39. So this is the important things you have to keep it in your mind, that the range of the lower IP and the range of higher IP, this you can able to determine based on the adding the number of zeros in the host sections and number of ones in the host sections. Thereby by adding a number of zeros in the host sections, you will be getting a lower type, and number of adding a ones in the host section, you are going to get the upper address. So this is what the example with respect to the distribution of the IP. That is what you can see, 32 to 47. This is your decimal representation, binary representation. Let's see the another example. Find the number of addresses in the above example. So how many addresses you can try to see in this case. So if you take n is equal to 28 with respect to the same problem, so you will be seeing that since the n is equal to 28, so it is indicating that maximum you can go as 32 minus 28, that is 4, that is 16 addresses you can able to do. So if you add 16 to this one, 32 plus 16, it is 48. So 1 minus that is 47. So you can have a 47 address. Mask. Mask is the way you can able to find the first address and the last address. That is why here what we have seen in this example, by calculating the bit level, and we try to identify. But in the mask we use the AND operation or OR operations to find out the first address and the last address. And this is particularly useful when we write a program to find a piece of information. So in the programming, in the programs, software programs, when you are using this technique, it is easy to identify the IP address at a various point where it resides and how to identify that locations. Now coming to the next example, let's see. Apply a mask to find the first address and the last address and the number of address for this one. So if you try to see this particular example, it was like the previous example, but here we are used the masking rather not like conventional methods of 8421 codes. Now here address is given. This is the address of representation of this decimal dotted into a binary dotted representation. Binary representation. So decimal dotted has represented to binary representation in this way. Now we have used the mask. Now you can see this one. This is which class? Class C. So class C, these three things is your net ID, and this is your host ID. So you can see this one from here to here is your net ID. So it is all 1112 255 255 255 255. That has come here. Now at the last point you have to apply mask. Now how you will be applying mask? You have to remember that what you had done in the previous example is that to find the first address you have made all the last 4 bit zeros. So you are making all the last 4 bit here zeros and the remaining bits as 1. So when you do that one, any bit when you are using here AND operations, so in the AND operation any bit is 0, it is going to be the same, and any bit is 1, it is also going to the same under the condition when all the bits of the mask is 255 or 11118 bits, the same address is going to appear, same address is appear, same address. Only here it is going to be a reverse. So in this case this is become 0, this is 1, and remainings are 0. So if you convert this one, so this is equal to the 32 bits. So that is what you can say 1 2 3 4 5 1 1 2 3 4 5 6. So this bit has occupies the positions with respect to the case of 64. This is 64, it is occupying the positions. So that is what we can find in this particular form of a masking. And the another case, if you try to see the ORing operations, in the ORing operations what we try to do is that we try to do the same in a reverse way, is that we do the last 4 bit as 1 and try to do the OR. So when you try to do the OR, all the zeros is going to wherever it is doing a zeros, it is remaining the same, and here in this case same. Here in this case it is going to find the same value of the uppercase also. So here you will be finding the value which is equal to 10110. So here it is how much? It is 7 here, and it is 8, 16 and 32. 7 plus this is going to be the 39. So that is we try to see in this particular order, and the number of address that can be found by complementing the mask. If you are doing a complement of this one, then it comes as a 15. That is 15 plus 1, 16 different combinations you can able to form using this particular scenario. So that is what we see in the case of a ORing operations, and in the case of a in the case of this particular scenario. So the example with respect to what we have seen in this particular scenario is 1 2 3 4. Here we have taken a 29 as the value, because here it is 7, and here it is 1 2 3 8 16 and 32. So this value is little different. So this is coming as 39. So here it is a 29. So this is for your correction. This is from 39. You can do it. Is not exactly the same example of it has a value with respect to the 39. So since it is 39 is there, so that 39 will be getting a initial value as initial value after doing with respect to this particular masking scenario. You will be getting a value which is, if you look across this one, this 39 and this mask, you will be getting here 1 2 1 2 4 8 16 and 32. So 32 you are getting here the value as the first case, and the next the second case, if you try to see the value, you are going to get it as again here it is going to how much it is. Here it is 16. See, because 8 plus 4 12 plus 8 plus 4 12 plus 2 14 and plus 1 15. So that is up to 15 values, and 15 plus and this one 16 not 15 plus 13 32. So it is getting as 47. So that 47 you can see here in this particular scenario. So we are having a 42 on the one side and 32 on the one side. So that is what we try to see in this particular scenario also. So that is what we see in the case of addressing. Now we go to the another examples. Before we go to the that example, let's understand this particular figure. Now here 28 bit, 4 bits. So 28 plus 4 is 32. So if you are using this way, so 28 means what? It is beyond the class C. So because let us say we are taking a class D scenario. So and here we are taking creating a net prefix. So this is a 28 bit and 4 for the host bit. So this is a 2-level structure is being configured. Now if you look across subnetting mask, what you can see here, this is a subnet 1, subnet 2, subnet 3. So you start with slash 27. See here it is given slash 27. Slash 27 it indicates that 32 minus 27, that is 5. So 2 to the power of 5 means 32. So you have a 32 combinations with respect to the distributions of this one. So you can try to see here. It starts with 17.12.14.1. So it is going up to 17.12.14.31. So that is a 32 distributions is there. Like that you can identify here also in this one. So here it is a 28. 28 means 32 minus 28 is a 4. That means you are having a 16 different combinations you can see across these particular sections. So that's how similarly you can try to see this distribution. So every distributions is being shown here. 3-level case hierarchy of IPv4 means you are having a net ID, you are having a host ID, and in between you are having a subnet prefix. So one subnet or a 2 subnets you try to create. One subnet means when you say one subnet means you create a one partition to one partition. If you are creating a 2 and 3 subnets, so you go for this one 1, 2, and 3. So that is not 2 and 3 subnet distributions. Now let's see an examples with respect to this particular scenario. What this example it talks about. Now here in this example, for this group, each customer need a 64 address. This means that 64 means what? If you take a log 2 to the power of 64, that is equal to 6. That is 2 to the power of 6 bits are needed for the each host. So we have to create a IP distributions for a 64 different customers. So that 60 each customer should have a 64 address. So this is what we have to do, and we are doing this example based on one selections of a one network IP will be there, that is a 192.168.0. So this is our way of solving this problem. So to understand this particular example, the best way is that let's see the starting statement. The prefix length is what? 32 minus 6. 32 minus 6 is nothing but 26. That is the prefix length. Now you may be looking at where this 6 has come, because 64 addresses is needed for a customer. As if one customer is asking that, say one company is asking to internet service provider, I need a 64 addresses for my, or Vidya is asking to a internet service provider that I need a 64 different addresses for my 64 different telephones. Think like that, or for 64 different computers. So that is how. So here 64 means it is if you are taking a 64 address, that is equal to 6. So that 6 bits. So these 6 bits are needed for each host. That means every host that is there, it will be having will be having an address based on the value of 6, that is 2 to the power of 6. This 64 different combinations we can able to create. So from 32, 32 is the IPv4 bits, minus 6 is nothing but 26. So this is nothing but /26. So the third group has 128 customers. So this is what it is given, 192, 100, 128.0. Now what is 192? Which class? It is a class B address. So these two are a network ID and these two are a host ID. So you can see in this case the 192 and the 0 is there. So this is not 55, 192. So that means this is a network distribution system. That means before this one, whatever is the earlier or that has been already given by the internet service provider to different other customers. So it starts with this address. So here the number of granted address is how much total? 2 to the power of 16. That means to 65,536 different service provider internet service provider is to grant. Why it is this much 200 internet service provider, how it has got this much value? Because based on the class B configuration, you are having the net ID is 16-bit. So the internet service provider can provide this much addresses. But here we need only this customer need only 64 address. So but service provider can give this much addresses. So that is this is the distribution possibility in the class B. So number of allocated address in the ISP is equal to 90,660. So this 90,660 has come from 16,000. It has come. Another it has come from 16,343. Another is from 8192. That means from this one 16,000, from this one another 16,000, from this one 8192. So this is the total ISP address in the case of a internet service provider for these customers. So the available address, what is remaining is this minus this is nothing but the available address in this particular scenario. Let's see this particular example. Now this slide has gone in a reverse way. So this is the C part. To understand this particular case, let's see this one. This is what been given. The question is that one, the internet service provider given this IP 190, 100, 0 and 0 /16. So from here we have to find the ISP need for the distribution. That means the first group is having 64 customer, second group is having 128 customer, third group is having 128 customers. And first group has 64 customer and each needed 256 address. That means in the 64 customers need 256 address each. In this one 128 customer, each will be needed a 128 addresses. Here 128 customer and each need a 64 addresses. So this is what we try to see. Now design a subblock and find out how many addresses are still available for these allocations. That is what we have seen in the final. We will come to the final in the after understanding this. Now the starting. First we are going with this one, 64 customer and 256. So we go with the 60. How many addresses is needed? 256. So 256 to the log 2, if you take, it is 8-bit. So this 8-bit we are going to find the prefix length. So prefix is nothing but this one, or slash, what we term it as. So prefix length is 32 minus 8 is 24. So 24 we have written here. Okay. Now from when we try to get this 24. Now if you apply in a reverse way, previously from 24, once we know /24, what we are doing, 32 minus 24, we get 8. 2 to the power of 8 is 256. That is what I have written here. It is same as this one. That is a reverse forward way, and this is a reverse way of combining. So the first customer will start from 192, 0 and 0. That is what is being shown here, and it will go up to maximum how many? 255.64. That means this is you only see this one. You don't worry about these things. So the first customer we will be getting 190.100.0.24 to 255. So that is what. Now you may think that why it is like written like this, because first here what first group 64 customer each needs 256 address. That means from 0 it has gone to 255, that is 256 it is got to the first customer. Like that 64 customers will be there. So for writing a 64 customer, we gone with the third group, that is 0, 1, 2, 3 up to 63. So this is 64 customer. Each customer is having a 0 to 255, 0 to 255. That is how we can get 64 customer, and the 64 customer into 256 addresses, that is equal to 16,348. So this is 16,348. It shows the different allocated addresses for the first customer. Second customers, if you try to see the second customer, it how many customer 128 customers, and it need to distribute the addresses for each customer is 128. So here also log to the power of 128 is 7, 32 minus 7, so we get a prefix address length is equal to 25. So 25 we written same thing, it start from 64. You see the case is that in the previous case it end with 63. So now we go with 64 and it start with the 0 and it will go up to how much, 128. So that is 0 to 127 is there. And how many here? Here also 128 customer. Again it is 0 to 64 to 127. So that is being shown in this particular scenario. So that that's the distributions, and 0 to 128 it is being shown here also in these distributions. So this is how the distributions with respect to the different customer it is being shown in these particular scenarios also. Now here 128 is here and 128 customer here in this case. So here you get it as 16,384 scenario. So this is how the distribution is shown with respect to the second scenario. The third scenario is being shown here. Now in the second scenario we got the maximum is 127. Here also what is in the third scenario, if you look across the third scenario case, it says that 128 customer and 64 address. So 64 address means it is equal to 6. So 32 minus 6, you got 26. So you got it in the prefix. So 128 to you are going 0 to 63 you have got, and here 128 you are 0 to 192 you have got it. That is the representations with respect to the additional bit with respect to the distributions of the 128 customers. So so here 0 to 63, 64 to 127, like that 192 to 255. But here also if you go, it has gone up to 159. So this is how we do the distribution. So 128 customer is there and 64 customer. So it appears as a 8192. So that is what we have seen in the previous case 1634. In the second case we found it about 128 customers, and in the third case you got it as another 128 customers, and thereby you have put down in this one in the group 1. You can try to see the customer 0 to 63, and here 64 to 127, 128 to 129, and also here also you can try to say you can try to see the representation of zeros also. It is being shown with respect to distributions 0 to 128, 0 to 192. Here also 0 to distributions with respect to the 0 to 63. That is the distributions in the first case also. So that is what you can see here, 0 to 190.1.0 to 0, 192 plus 192, 1.0 and 0, and it has gone up to 255. Here also 255, here also 0 to 255. Here you can see 63, 127, 159. It is being shown over here 0, 64, 128. So available is this one. That is what we can try to see here in this example. And finally, we have another examples. Before we two more example, let us see. In the one case is that here an IP is given, and from this IP we have to find out network IP, fourth host, last host, broadcast hop. Now how will you find out this one? Now in this IP, your IP is there. Which IP is this one? If you see this one, this is a class C. Class C range from 192 to 223. So your IP, you have got it this one. So this is the first octet or the network. Now from this IP, you are doing the masking, because this is a class C, so these three things will be 255. And you have got the first IP. Now from here, you have to find the fourth host. This is your network ID. This is your first, you are going to find the network IP. So network this is the network ID scenario is that this is, assume that this is like a network. So this is 220, 30 and 0. Now we have to identify the fourth IP ID or the fourth IP. So how will you know? So this ID is network ID. This you cannot touch. So you can start with 1, 2, 3, 4. So this is your fourth host ID. And what is the last host ID? That one, how will you able to find out? To find the last ID, what you have to do is that you have to go up to 255. That is the last. Maximum you can go up to 255. You make it all once and you do the masking. You will get the last host ID as 201, 20, 30 and 254. So 255 means one less, 254. Now why it is one less? Because we started with a 0 here. That's the reason. Now we go with the another is that broadcast IP. Broadcast ID ID or IP is nothing but two type. One is a limited type, another is a direct broadcast. Limited type means it will broadcast within the network. Direct broadcast means from the other network it is accessing the broadcast IP. That is what it means. Here the own broadcast IP is distributing all the information to every student. Think. Another is that another network or another institute want to pass information to our students. So they will access this network. That is what you can see here. In this case, the broadcast IP is nothing but the last IP, that is 255, 255, 255, because this cannot be used by any host. And if it is a direct broadcast scenario, we go with same 255, 30, 54, 30 and 254. Instead of that, we write 255 because 255 is the last ID, last host ID will be there. So that will be not accessed by anybody. So that will be considered from the outside network to inside. Whereas inside it is, we can straight away go with this side. So this is what we see with respect to the case of a IP given, but we have to find out network IP, the fourth or a second, whichever host IP, last host and the broadcast. We see another example with respect to the subnets is that find out the subnet and the number of valid per subnet. And that means if we have given one IP, and from that IP we have to find out the number of subnets and number of valid hosts. What is valid host? Whenever our net ID and the host ID, if it is a valid, then that is what we termed it as a valid host. So here subnet is, if you want to find out, this is a formula. Subnet is equal to 2 to the power of subnet bits. That is what. And if it is a valid host, 2 to the power of number of host bit minus and 2. 2 to the power of number of host bit minus bit. So this 2 bit, why it is 2? Because for the network number and for the broadcast address, these are not assigned to the broadcast address, this is not assigned to the host, and the because of the network number we are keeping that one minus 2. Now here the IP is given 192.168.1.0. So we are creating 192 means class C. So this is class C. So these three are net ID and this is host ID. So our mask is having this 255, 255, 255, and here our the host ID is 240 because we are keeping the 4 bit 0 and this one 1. Why it is? Because here we are going to show that 32 minus 24. So 32 minus 24 is how much? It is 4. So since it is showing a 4 bits, so that 4 bits we have to show, consider as 0 based on the conditions that because of the 34 minus 24, 28 is equal to 4 bits. So that 4 bit is used for finding the address. So when you do this, when you do the masking for this case, so subnet is nothing but 2 to the power of 4 is nothing but the 16 subnet is being created. So in this case, that means the total subnet is possible in the case of 2 to the power of 4 is 16. And what is the host? 2 to the power number of host bit minus 2, that is 2 to the power of 4 minus 2 is 16. That means 16 minus 2 is a 14 valid host bit you can able to create in this particular scenario of a class C. So that is what we talk with respect to the host scenario. And here number of subnet bit is equal to 4 based on the your case and the situations with respect to the we have seen with the prefix situations that is existed in these particular conditions. If you take another example 150 0.0 and using the /30, now here also if you do the masking, this 150 is a class B, so this is having a 2 bytes for the net and 2 bytes for the host. So if you do this one under this particular scenario, how many is possible? This 14 bit you are taking because 32 minus 2 is 30. So that 32 minus 2 is 30 we are not taken into considerations. So that 2 bits we are trying to avoid, rather we are taking a 6 bit. So that 6 bit here and here it is 8. So 8 plus 6 14. So 14 bits means subnet is equal to 2 to the power 14 is 16 16384. That is that combinations, that is what we see. And another is nothing but 2 to the power of a 16 that is minus 2 is nothing 2 to the power of a 2 minus 2 is nothing but 2 valid bits. So that is what we try to see the combinations with respect to the second case with respect to the number of a valid host bits. So this is nothing but your number of valid host bit we can create using this particular example. Here is an example, final example with respect to the IP subnet. Whenever you are having a IP address like this one given, so and if your total IP address in this particular case, since it is a class C, so let us take the 2 to the power of 6 is nothing but a 64 combination. So total number of a host 64 minus 2 is nothing but a 62 bit. So your range of IP address starts from this to this, that is a 0 to 263. second subnet case with respect to the same total IP address is up to 64. So if our range goes from 64 to 127. Third case, third subnet, if your IP address, total IP address is 62, then it starts from 128 to plus 62. That's how it goes to 191. Again, if it is a 64, it goes from 192 to 55. So this is showing how the subnet is being distributed into different IP range. So that range here it is shown for your understanding, binary representation here, but actually we should write in this way for your in real sense. So first subnet distribution, second subnet distribution, third subnet distribution, fourth subnet distribution. So these are the basic discussions that we have seen in this numerical. Let me summarize that we haven't gone through the class full addressings. We have seen the subnetting addressings. We have seen that an example related to the how the binary is converted to a dotted decimal and how dotted decimal is converted to a binary notations. We have seen that different type of error in the addresses. We have also tried to see that how the organizations can able to find an address, and from there using a prefix we can able to find the back address and the front address. That is what we have seen. We have seen the same problem using a maskings also, how the masking is done based on the class. Then we have seen that how the organizations is distributed with respect to the customer and the number of address, and how that distribution is being classified from the ISP perspective and its distribution, and finally how much they are retaining. So and finally we have seen that by having a IP address, how to find the network IP, host IP, last host IP, broadcast IP, and also about the subnet distribution. So with this I come to the conclusions with respect to the numerical problem. More on these numerical problems will be coming by looking across the different reference books, so that you can able to try and practice the network IP related problems, so that you will be well tuned to that one. And this is the very important sections. Thank you.